Okay, today we're going to introduce probability, and your essential question is, what is probability? So we've got a scenario here. We usually, with probability, a lot of times we use dice. Suppose two dice are rolled, one white and one black. Figure 14-1A shows the 36 possible outcomes. So they've just kind of laid out, if you roll the dice and you get a 1 and a 1 if both die are 1s. There are 5 outcomes for which the total on the dice is 6. Now, this actually is kind of interesting. So if you lay out the diagram to look like this, if you're looking for all the ones whose total is 6, well, here's one whose total is 6, right? And then every other one's going to be in a pair, in a diagonal. So every other pair of 6 is also going to be in this exact same diagonal. So it makes it kind of easy to find, which is really nice. So we have 5 outcomes whose total on the dice is 6. And because each outcome is equally likely, you would expect that, right? So basically these dice, it's equally likely that you roll a 1 as it is you roll a 6, or you roll a 2 as it is you roll a 3. It's not like there's a die that has like 3 on all sides. Then the probability would be 100% that you'd roll a 3. So then you would expect that in many rolls of the dice, the total would be 6 about 5 out of 36 of the time. This number, 5 out of 36, or 536, is called the probability of rolling a 6. And that's basically what we're going to talk about here. So this is what we would call the probability of rolling a 6. I'm just going to go ahead and highlight that probability. We'll talk a little bit more about that. Okay, so first of all, let's talk about some vocabulary here. So a random experiment, such as rolling a die, is that you have no way of telling beforehand how it's going to come out. I roll a die, I have no idea which number I'm going to land on. So no way of telling beforehand how any trial is going to come out. And then the outcome. So the outcome is basically the result of a random experiment. So the outcome could be I roll the die and I get a 1. Or in these cases, I roll 2 dice and I get a 6. That's the outcome. So it's the result of a random experiment. Now, an event is the set of one or more outcomes. So an event is set of one or more outcomes. So for example, in our example here, the event would be the total when 2 dice is equal to 6. So this is total of 2 dice is 6. And so what we have here is we have a 5-element set. So here we've got 5 times when this outcome happens. So our event is really a 5-element set. Okay, so there were 5 times that it happened, so we're going to say our event is happening 5 times. It's a 5-element set. And then the sample space is the set of all the possible outcomes. Well, how many total possible outcomes were there in our scenario here? There were 36, right? So here, for example, we have 36 outcomes in the set of the dice rolling experiment. I'll abbreviate experiment. Okay, so that's just a little bit of vocabulary. And now we're going to actually define, so the definition of what probability actually is. And you know this, we've done this before. You have definitely done this. We touched on it in Algebra 2, we touched on it in Geometry, you probably even touched on it in Algebra 1, and definitely probably at some point in your junior high career you also talked about probability. Okay, so if the outcomes of a random experiment are equally likely, then the probability that a particular event will occur is, and it's really simple. Probability is always going to be the number of outcomes in the event, so the number of favorable things, the things that you're looking for. For example, in our example, it was how many times will our two die roll and give us a sum of 6. And so for that, it was 5 times. And then the number of outcomes in the sample space. Well, the sample space is all the possible outcomes. So the number of outcomes that we had were 36. So for our example, we could write something like, and this is symbolically, so the probability of an event occurring is the number in that event, and then so the set, let's see, so how do we say that? The elements in the set, okay, and we had 5 there, over the number of total sample space. And for us, we had a total of 36, which we talked about down here. So to write this probably in a way that looks more mathematical, we're going to say, what's the probability of rolling a 6? Okay, so that's how you'd write it. The probability of the outcome that you care about. Now, I'm going to say it's the number of the outcomes in the event. Well, in our event, the number of outcomes was that it was 5 of those outcomes, right? 5 of those outcomes, we had a 5-element set for our event. So we're going to say this is the number of basically rolling a 6. So how many outcomes do I have where I actually got a 6 out of the number of the total? So that's how probability works. It's like your favorable outcomes out of your total outcomes. And we're just using a little bit more complicated vocabulary here. And the number of my favorable outcomes, or again, the number of the set that was in that event for this scenario was 5. And then our total number, or the total outcomes in the sample space, was 36. So that's pretty simple. So another way to think about this is like favorable outcomes out of total outcomes. Okay, and then I'm going to do one problem with you from your text. I'm going to do number 2. Let's see what page that is. Page 707. So this is in 14-2, I thought. Oh yeah, 14-2. So this is number 2 on page 707. All right, so you've got a penny, a nickel, and a dime are flipped at the same time. Each coin can land either heads up, H, or tails up, T. So assuming that basically these are just normal coins, we'll do A first. So what term is used in probability for the act of flipping the coins? Well, we just went over that term, right? There's no way of telling when you flip a coin whether it's going to be heads or tail, as long as you're flipping it and not cheating, right? So the term that basically would describe this is in our notes right here. We have no way of telling beforehand how it's going to come out, right? If we flip that coin, we have no idea. So it's really going to be a random experiment. So I'm going to write on this piece of paper here. Okay, moving on to B. So one possible outcome is tails, head, tails. List all outcomes in the sample space. And one really useful way of doing this is to use like a tree diagram. So what you can do, let me give you this back. What you can do when you use these tree diagrams is you can say, okay, I know I've got a penny, I've got a nickel, and I've got a dime. So my penny that I have can either land on heads or it can land on tails. Then, based on that, my nickel will do the exact same thing. It's either going to land on heads or tails. Right? So if my penny lands on heads and then I flip my nickel, well, my nickel's either going to land on heads or tails. And then I go over and I flip my dime, and that's either going to land on heads or tails. Or maybe my nickel landed on tails, and then I flip my dime, and I get either heads or tails. Now I can do the same thing. What if my penny instead lands on tails my first time around? Okay, then I go back and I flip that nickel, and I either get heads or tails. And then from there, my dime will either land on heads or tails. So right here, if I look at all these extended branches over here, these are going to be the total possible outcomes. So basically my sample space. So I'm going to go ahead and list them. So I can get heads, heads, heads. Oops, you can't see that. There we go. Heads, heads, heads. I can go heads, heads, tails. I'm going to list them down. They're a little bit easier to see if you write them downwards, but you can also like list them with commas. Okay, so I went heads, 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 tails, heads, tails, head, heads, tails, tails. Okay, so I think I got all the possibilities with the penny landing on heads first. Now let's go to tails. So we can go tails, head, head. You can go tails, head, tails. You can go tails, tails, head. Or tails, tails, tails. So I've just listed all of them. And how many total? So you can count your branches or you can count them right here. But basically I end up with a total of 8. So there are 8 total possible outcomes. Let me read the question again and see what they're saying here. One possible outcome is tails, head, tails. List all 8. Yeah, so I've done it. List all 8 outcomes. Great. Done. Now, what's interesting here is, give me one second. So this is there are 8 total outcomes, right? Now notice that on every single coin, I had 2 possible outcomes. So, there were 2 possible outcomes here, 2 possible outcomes here, 2 possible outcomes here. Notice that 8 is the same as taking 2 times 2 times 2, or 2 to the 3rd power. So that could be another way that you could figure these out without drawing out the tree diagram, right? You think about every single event that you're doing, and then you think about, okay, what are the possible outcomes for that? So just one, another way of thinking about this. So a penny had 2 possible outcomes, nickel had 2 possible outcomes, and a dime also only has 2 possible outcomes. So I take 2 times 2 times 2, that gives me the total number possible of outcomes, or sample space. All right, moving on. How many outcomes are in the event? Exactly 2 of the coins show heads. Exactly 2 of the coins show heads. Now I'm going to write this so kind of in probability like notation. So you could either say the probability or, oh no, we're not doing probability yet. We're just looking for like that, what's the proper vocabulary? Let me give you the number of outcomes in the event. Okay, so we're looking for exactly 2 heads. So that's how you would write it out. Okay, and then we're looking for, and we just go through here and we're like, there's one, there's one, there's one. Okay, so we got 3. We're not even finding probability here. We're just finding the number in the event, the outcomes in the event. Okay, D. Calculate the probability of heads, heads, tails. Probability of heads, heads, tails. Oops. So now we're actually looking for the probability. So again, we're looking at, right, taking the number of the outcomes in the event over the number of outcomes in the sample space. All right, so how many heads, heads, tails do I have here? Well, it looks like I only have 1, right? So that's really going to be the number of heads, heads, tails out of the numbers of your sample space. All right, well, I've got 1, and the number in my sample space was 8. Should probably be circling these so that way they stand out. Okay, next problem. Would like to know the probability of exactly 2 heads. Well, the probability of exactly 2 heads. Well, let's find how many of these have exactly 2 heads and then put it over the sample space. So let's see, 2 heads here, 2 heads, so 3 out of 8. Oops. Okay, now this one's a little bit different. See, that was exactly, this is at least 2 heads. So you can have 2 heads or you can have 3 heads. So F is to calculate the probability of at least 2 heads. All right, well, I already had 3 that were 2 heads, exactly 2 heads. And then I've got 1 more that's 3 heads. So I think it's 4 out of a total of 8, which is 1/2 or 50%. Right? A lot of times when we talk about probability, we actually don't talk about fractions a lot of times. We talk about them in terms of percent, because a lot of people can understand that more than fractions for some reason. They are the same exact thing. All right, G. Calculate the probability that a penny and nickel are tails. So this is probability penny and nickel are tails. All right, so it goes penny, then nickel, okay? So, and then we need both of them to be tails. So it looks like I've got 2 possibilities here. So 2 outcomes in my event give me where penny and nickel are tails. So that would be 2 out of 8, or 1/4, or 25%. Next one, calculate where the penny or nickel is tails. Okay, so or means a penny can be tails but not the nickel, or vice versa. So the probability that we have a penny or a nickel tails. Well, I think that's going to give us more, right? Because the penny can be tails here, basically all of those. The nickel can be tails there as well, but there's also a couple more here, right? So I think it's going to be all 6 of these. Or 3/4 of the time, or 75% chance. Okay, I think I'm running out of room, but I will figure that out in a minute. I calculate the probability that none of these are tails. I'm going to do one more right here. So probability of no tails. Pretend like I spelled that right. Well, when I look at my list, there's really just one outcome in which there's no tails, and that's the first one. So that's 1 out of 8. I think I'm just going to go over here. Let's do J over here. Last one. Oh, no, I lied. I got 2 more. Calculate the probability of 0, 1, 2, or 3 heads. Probability that we have 0 heads, 1, 2, or 3 heads. So 0 heads, 1, 2, or 3 heads. Well, that's all of these, right? So that's 8 out of 8, or in other words, 1. So I'm going to do probably 1, 2, 3 heads. And that's going to equal 8 out of 8, or 1. And really, that's 100%. So if it equals 1, that's 100%. And then the last one, we got one more here. Can you guys see that? So then we're going to calculate the probability of having 4 heads. Calculate the probability of 4 heads. So we'll do the probability of 4 heads. Well, how would it be possible to have 4 heads? We don't have 4 coins. So that's a very simple 0. And what we would call the empty set. We basically 0% chance because we don't have 4 things.